Welcome back, class. Now today I want to wrap up what is our last segment of this semester. This will actually be the last video that I'll be recording, talking about one specific section of chapter 13, and that's 13.4, where we just do a brief survey of the types of crystalline solids. So we're going to focus on crystalline solids here, and we're going to look at the various types, and we're going to look at how the type of interactions, whether it's intermolecular forces or bonds, how that translates into melting point, or maybe some other properties if we see something. Okay, so first of all, let's just look at the big picture. So big picture, there are three types of crystalline solids, right? We have molecular solids, we have ionic solids, and we have what are called atomic solids. And we will look a little more detail at atomic solids because there are three different types of atomic solids. They're what we call non-bonding atomic solids, metallic or metals atomic solids, and what are called network covalent atomic solids. So these are, of course, going to be, elemental solids, right? These are the different elements on the periodic table that exist as solids. They fall into these different categories. Okay, so that's the big picture. Let's do a survey. And then I would encourage you to sort of, keep this chart in mind, a reference as you're going through the rest of this, and then you can refer to some of the basic points on this chart, so where they fall on this spreadsheet, if you will, this flow chart. Okay, so let's start with molecular solids. So these are the common molecular materials that we're, been studying, right? These are the solid forms of things like water, right? Ice, or carbon dioxide, dry ice, right? Or any other molecular materials, right, that exist as solids, right? Things like sugar, right? So these are solids that are composed of molecules, right? And those molecules are, of course, connected by various types of intermolecular forces, right? That's what holds the molecules together. So when we melt these materials, this is what we need to break. So as we've talked about, as those intermolecular forces become stronger, the melting points will tend to rise, right? So we're going to look at either dispersion forces or dipole-dipole forces or hydrogen bonding to give us the type of intermolecular force that we have to break. Now, we'll look at ice as our example, right? Ice is held together by hydrogen bonds, right? And dry ice is held together by dispersion forces. And as we looked at earlier, ice has a melting point of 0 degrees Celsius, much higher than the sublimation point, right? Again, it doesn't melt at atmospheric pressure, of dry ice of minus 78 degrees. So the much stronger hydrogen bonds in water versus the dispersion forces in carbon dioxide, right? It's a nonpolar molecule, result in the much higher melting point of water or of ice compared to the sublimation point of dry ice. But in general, molecular solids will tend to have low to moderately low melting points, right? So under a couple hundred degrees typically. So again, low, on the low side, if you will. Now, ionic solids. Again, we're quite familiar with these class of materials, right? So these are our ionic materials that we think about, sodium chloride and any of the other, ionic compounds that we've talked about. Now, remember what they're composed of, right? They're composed of not molecules, but they're composed of three-dimensional crystal lattices made up of the positive and negative ions. where these ions are connected not by intermolecular forces, but by ionic bonds. And of course, ionic bonds, just like covalent bonds, are much stronger than any type of intermolecular force. And so, when you melt an ionic compound, you have to break these ionic bonds. Of course, that's going to take a lot of energy. And so as a result, something like sodium chloride has a much higher melting point than something like ice. And in general, ionic solids will tend to have much higher melting points than molecular solids. And just to give you a number to look at, sodium chloride melts about 800 degrees, right? Compared to ice at 0 degrees, right? Or other molecular solids at, sort of temperatures, below 100 degrees or so. Now, those are sort of our two standalone, right? And you notice those are kind of the big bulk of the compounds that we've looked at, right? Ionic compounds, molecular compounds. Big difference, one's held together by relatively weak, in the scope of things, intermolecular forces, whereas ionic compounds are held together by much stronger ionic bonds. Now, atomic solids. Well, again, we have to break these down a little bit more before we start to look at them. So atomic solids, of course, are composed of atoms, right? Not molecules. And so they're made up of individual atoms. So these are things like diamond, right, which would be a form of carbon atoms, or iron, right, which would be, an example of a metal, individual iron atoms, or even solid xenon, right, a noble gas, right? Or, which are going to be, different, fall into these different categories. So atomic solids, again, 3 categories. We have covalent atomic solids, right? And these are going to be, oops, and I didn't type it in. These are often called network solids as well. So you'll probably hear the term network solids or read the term network solids, and that's the same thing. That's covalent atomic solids. We have non-bonding atomic solids, and we have metallic atomic solids. So let's look at each of these. Now, from this basic chart, we can just sort of get the basic idea. So non-bonding are going to be held together by dispersion forces. Network solids or covalent solids are going to be held together by covalent bonds. And metallic solids are going to be held together by what's called metallic bonding, or metallic bonds. But let's look at these in a little more detail. So, first of all, let's start off with our covalent or network solids. And the big examples here are things like carbon, right, which is just this diamond, and also graphite, both examples of network solids. Quartz, right, which is a form of silicon dioxide, right? Or silica, right? Sand, right? So another example of a network solid. Now, these in various forms are going to be held together by covalent bonds. So the carbon atoms or the silicon atoms are going to be held together by covalent bonds. Those covalent bonds, of course, are very strong, just like ionic bonds. And so network solids are going to have very high melting points. Now, at the sort of extreme, diamond is going to have a melting point estimated at almost 4,000 degrees, 3,800 degrees, right? If we wanted to melt diamond, right? It takes a lot of energy to break down all of the intermolecular forces that are present, all the covalent bonds that are present within diamond, right? You can look at, if you look at the blow up here, you can see that each carbon is in a tetrahedron surrounded by other carbon atoms. So 4 covalent bonds surrounding every carbon atom to 4 other carbon atoms. High melting points. Now, I'm going to point out now, I'll try to remind you at the end again, I'm going to post a supplemental video that has to do with network solids. Focuses a lot on graphite and diamond and the differences. And I say it's supplemental because we'll take some material from that potentially and use it as the basis for maybe an extra credit question or two on the final exam. But I encourage you to listen to it. You'll learn some more about network solids specifically, but just in general, and a little bit more detail, a little bit more insight into the differences between diamond and graphite. Now, there's another supplemental video from the same source. These are crash course videos that deals just with solids, and that one is part of sort of the general course, not supplemental. Okay, so that's covalent atomic solids, held together by covalent bonds, high melting points. Non-bonding atomic solids are sort of on the opposite end of the spectrum, right? These are going to be the examples such as the noble gases like xenon. These are held together by dispersion forces, so weak, interactions. Now, they're stable, so they don't form covalent bonds, and that's why we only get dispersion forces, right? They have no reason to bond, right, with other xenon atoms or any other atoms for that matter, for the most part, right? And so they can't form covalent bonds with other things, so they're just hooked together, kind of like other non-polar molecules might be with these dispersion forces. And as a result, these non-bonding atomic solids have very low melting points, well below 100 degrees. And so xenon melts at negative 112 degrees Celsius. Now finally, metallic atomic solids. So pick a metal, right? Lots of examples here. Iron, silver, lead, right? The big take home here is they have variable melting points, right? You will have metals that melt low and melt high. So let's talk a little bit about what holds them together. Well, metals are held together by what are called metallic bonds. Now, these are different type of bonds than what we've talked about. We haven't spent a lot of time, we won't spend a lot of time in this course or even next semester talking about metallic bonds. But the easiest way to envision them is what's called the electron C model of bonding, where we envision the metal atoms as cations, right? So they've lost their electron, or lost electrons, so they form positive islands, if you will, right? And the electrons that they've lost are delocalized, so they have the ability to move, from one island to another, right? They're not linked specifically to one specific cation. They can move, to various cations. And so this is why we envision this as called the electron C model, where we have these islands of positive charge, the metal cations, surrounded by this flowing sea of electrons. And of course, this model helps us visualize some of the basic properties of metals, like their ability to conduct electricity, right? Electrons can easily move through. We have mobile electrons within the metal. So those electrons can move from one metal cation to another. And so the electron C model, now the bonds between these cations, right? These are, between these electrons and cations, these are the metallic bonds, right? So there's attraction between the electrons, and these various positive centers give us those metallic bonds. Now, these have varying strengths depending on the metal. For some metals like mercury, they're quite weak, and so melting points are below room temperature. For other metals, they're quite strong, and so something like iron has a melting point of about 1500 degrees or above, right? Depending on, where you look, right? And other metals will even be higher melting points, and others somewhere in between, right? So things like aluminum, right? We can melt quite readily over a fire, right? Gold, right? We can melt it over, a fire. Iron, not so much, right? You take your Bunsen burner in lab, you could melt certain metals with that, but you're not going to melt iron, right? We know that, right? That we use iron on things that we heat it on. It doesn't melt it. It gets hot. Doesn't melt it. But other metals we're going to be able to melt. And so the bottom line is they have varying melting points. So if I look at this sort of big picture, what I want you to be able to do is understand and define what each of these are. We want to know what type, the basic characteristics of the solid, what's holding them together, right? So covalent bonds, ionic bonds, dispersion force, whatever it is. We want to be able to roughly rank them by melting point. Like if I were to give you, say, an example of a network solid, a molecular solid, and an ionic solid, that you could rank them and you would say, oh, well, the network solid, based on the examples I know, is going to have the highest, right? Because, the examples are up in the thousands of degrees. Whereas an ionic solid is going to be somewhere in sort of the middle, right? Hundreds of degrees, perhaps. Molecular solid is clearly going to be lower than that. And so we want to be able to sort of rank these based on not only what's in the table, but just sort of our basic experience. Okay, so that's kind of what I want you to do is a very descriptive look at what these metals are, what these solids are, and sort of where they fall, and the basic ideas about them that we've talked about. All right, so that wraps up the course in terms of my videos. Again, make sure that you try to watch these along with the supplemental videos to supplement what we're doing in class, especially now that we're not going to be meeting face-to-face. This might be even more important. But again, if you have questions about anything you hear in these videos, send me an email. We'll try to get it straightened out as we move toward the conclusion of the semester.